Hello Scala boys and girls, this is Daniel for Rock the JVM, and in this video I'm going to introduce the concept of fibers in Cats Effect 3 and some concepts of asynchronous computations on IOs in Cats Effect 3. Now, this video will assume that you're just getting started with Cats Effect 3. I'm going to code in Scala 3 here. I'm using Scala 3 RC2. And as recommendations, I'm going to obviously suggest, as always, to code with me in this video if you have the space. And whenever you need to refresh your memory about these concepts, just refer back to this video or to the written form at the blog with the links in the description. Alright, so without further ado, I'm going to jump right into the code and I'm going to teach you how you can use fibers and asynchronous IOs in Cats Effect 3. Now, my application here is an object called asynchronous IOs, and I'm going to make it extend IO app, which is the entry point in any Cats Effect application, and IO app is a trait that has a run method that takes an argument list, so args as a list of string, and this run method returns an IO with exit code. Now, exit code is a trivial data structure, but IO is the crucial data type in Cats Effect, and this describes any kind of computation that might incur a side effect and that might return with a value of type A. Now, this will be the focus of this video as well, and I'm going to show you how we can run fibers, that is lightweight threads in Cats Effect, and how we can abstract away those asynchronous computations with IOs. So I'm going to define a couple of IOs. I'm pretty sure you know them from the very beginning of Cats Effect. If you've read the first 3 lines of documentation of Cats Effect, you probably got accustomed to IOs. So an IO can be created, let's call this meaning of life, because I like the meaning of life, and I'm going to instantiate an IO with the apply method, and I'm going to pass in 42 here. This will be an IO of int. And I'm going to, for the sake of variety, I'm going to describe another IO because we're going to compose them. I'm going to call this favorite language as an IO string, and I'm going to have another IO with Scala. The string, that is. Now, an asynchronous computation on top of IOs is done with a data structure called a fiber. And I'm going to define a method called createFiber. And this will return a fiber type. And I'm going to have a fiber that I've already imported here. By the way, I'm using Scala 3 RC2, and for this RC version, IntelliJ is not really that smart and cannot import those types for me automatically. Once you write Scala 3, these imports should come up automatically if you hit Alt-Enter or Option-Enter if you write a type that's not known at this point. All right, so don't worry about that. And the fiber type takes 3 generic type arguments. The first is the effect type, which is itself generic, and I'm going to use the IO type. And then the error type that this fiber might fail with, and I'm going to use throwable. And the data type that the fiber might be successful with. If the computation computes successfully, I'm going to return, for example, a string. And I'm going to use the question mark value here because constructing a fiber manually is almost impossible. Creating fibers is done with various APIs in Cats Effect, and I'm going to show you a couple. Now, you may have heard of the concept of fiber or lightweight threads or virtual threads in Java, in the Java Loom project. If you've read that, I'm going to have a link in the description if you're curious. So these fibers are so-called lightweight threads. They are conceptually similar to threads in that they are scheduled and then they can yield control, and executing fibers concurrently might lead to non-deterministic results and so on and so forth. But the main advantage with these fibers is that unlike JVM threads, which can only be spawned in the thousands by a regular machine at best, with fibers you can create millions per gig of heap, and you can schedule millions of these without breaking a sweat, basically. Now, in fact, fibers that are described with this data type, fibers are not active entities like threads, like JVM threads. Instead, Fibers are passive, just data structures containing some code that can be evaluated on some thread spawned by the thread pool managed by Cats effect. So fibers are merely data structures that are scheduled for execution by the Cats effect scheduler. Now, just to illustrate the thread on which IOs execute, I'm going to define an extension method that, given an IO, will decorate that with a debug method that will also print the thread name so that you can be sure that they are executed on different threads. So I'm going to define an extension method that, given a type A, I'm going to decorate an IO as IOA, and I'm going to put a space here because I'm going to anger some people. And given an IOA, I'm going to define a method called debug that returns an IOA. And I'm going to have the IO.map. And given the value inside of this IO, I'm going to print line. And I'm going to use an S-interpolated string. And I'm going to inject the thread name. So I'm going to have thread current thread get name, so that you can be sure that the IOs that I'm gonna show you execute on different threads. So I'm going to isolate these by some square brackets over here in the format so that they are isolated from the value themselves. So I'm going to use value inside, and then I'm going to return the same value. So I'm not going to change the value at all, but I'm going to return the same value that the original IO had. All right, so I'm decorating all the IOs with this extension method called debug so that we can also print their current thread. All right, now just to start from a simple example, if I have meaning of life and favorite language, they are both evaluated on the single thread if I turn on this application. So let me define a method called sameThread. And I'm going to use a for comprehension here. So for I'm going to have an underscore with meaning of life dot debug and underscore in favorite language dot debug. All right, and I'm going to yield unit because I don't really care about the result of this thing. I only care that I print the thread name and the value is computed of those IOs. And in the run method, I'm going to call sameThread as exit code dot success. So I'm running this IO, which is an IO unit, and I'm forcing its result to be exit code success because I don't really care about the result of that IO. So now I can run this application, but as I mentioned earlier, IntelliJ isn't really that smart at this moment with Scala RC2 or RC3 or whatever you may have prior to the official Scala 3 launch. So I have a run configuration that runs this object as it is. So I'm going to hit Control R so that I can run this application. Now, if you're writing Scala 3 itself, then this should be really trivial for you. Just right click and then run. So notice that we have both IOs 42 and Scala evaluated on the same thread called IO compute 1. Now, I'm going to show you how we can make these computations, these IOs, actually defer to a different thread through a fiber. So I'm going to create a fiber, and I'm going to delegate the meaning of life to another thread. And the way that I'm going to do that is I'm going to say meaning of life.debug so that we can know where or which thread it actually runs on. And I'm going to call a very special method called start. Start returns a fiber with IO throwable and the data type wrapped in the original IO. So this is going to be a fiber with IO throwable and int in this case. But unlike other calls which start a thread, like start a JVM thread, or instantiate a future, which also automatically start the computation on another thread, the fiber itself is not started until I say so. And so this fiber object is also wrapped in another IO. So the result of that is going to be an IO of this fiber. So if you hover over this type, the compiler isn't really too smart. I'm going to add the type in here. So the IO is going to wrap a fiber which executes this IO. Cool. Now, I'm going to use this fiber to show you how you can delegate an IO to another thread. So I'm going to define another method called different threads. And I'm going to use another for comprehension, and I'm going to say underscore a fiber just like that, because a fiber is also an IO. And I'm going to have underscore in favorite language.debug so that we can see where or on which thread this favorite language IO is being executed. I'm going to yield unit, and I'm going to call this other method in the run method. Okay, now let me run the application with Control R. If you're doing a Scala 3, you might right click and run this application. Let's see how we got different results. So we have 42 in Scala, but notice that this time we have different threads computing these IOs. So if I do different threads as exit code success, the Cats effect runtime actually starts evaluating this IO, this different threads IO, which is an IO unit, and this starts the computation on the fiber on an actual different thread. So you see here that we have IO compute 9, one thread, and IO compute 10, which is the calling thread, the main thread, and this prints Scala. So now we have two different computations on two different threads. Now, if I also say a fiber.debug, now this will also print the value of the fiber itself on some thread, and I'm going to show you what thread that is. So I'm going to run this application yet again. So notice that we now have 3 lines, and we have IO compute 0, which is the calling thread, which is the favorite language, which was never asynchronous. The number 42 was indeed computed on another thread, and now we have a third line which is false, and this false thing is the value of the fiber itself. Now, in the guts of Cats effect, fiber extends atomic reference with a boolean, and that boolean is false in this case. So fiber extends atomic boolean with false, and this is why we see false here on the console. But what I wanted you to actually pay attention to is the thread on which the fiber itself is being evaluated. So the fiber itself is evaluated on the calling thread, and the IO scheduled by that fiber evaluates on another JVM thread. All right, so pay very close attention to these threads. Now, if you think about it, spawning a fiber from the calling thread is very similar to spawning a regular JVM thread from the calling thread, because you have access to the thread from the calling thread, but the actual code of that new thread executes on another JVM thread. So if I say new thread with some runnable, like printline something, okay, and I actually do proper spelling, this thread object is computed on the calling thread, on this main thread. But if I do thread.start, the actual code, the print line, executes on a different thread. And this makes sense, right? So we have access to the thread object from the calling thread, but the code inside executes on another JVM thread. So this concept is very similar to the thread on which the fiber itself is being evaluated. All right, now I'm going to show you a couple of things that you can do with these fiber objects. I'm going to define a method called run on another thread, and this takes, I'm going to have it take a type argument A and an IO as an IOA as a regular argument. And I'm going to say the following. I'm going to have a for comprehension, and I'm going to say IO.start. So this will return an IO fiber. So I'm going to have a fiber inside this IO, and this fib is a fiber. And with this fib reference here, I can call a bunch of methods. For example, I can wait for it to finish. So I'm going to say result left arrow fib.join. So join will wait until this fib thread has finished, and I'm going to yield result. Now, I'm going to call run on another thread with my meaning of life to see what happens. So I'm going to run on another thread, and I'm going to pass my meaning of life thing, and I'm going to call debug here as exit code dot success. And I'm going to add the debug after the call of the method so that we can inspect the result that we obtain after we wait for that fiber to finish. So I forgot that I don't have a run action here in my context, so I'm going to hit Control R to run my application again. And now we have my thread, which I don't really care about in this example, but what I care about is the result that we obtained. And we obtained not the number 42, but succeeded with IO 42. That is because joining a fiber will wait for the fiber to finish, and a fiber can finish in one of three states. It either succeeds, so that is the success with an IO with 42, in this case, with some value. It can fail, so that is a errored with an exception. And the third case, or the third state that this fiber might end with, is cancelled. And I'm going to talk about cancellation in a further video, and definitely in the Cats Effect course that I'm preparing for you guys. But these are the three main states that a fiber can end with. And this success with an IO value is the result that we're seeing here. I'm going to give a bunch of examples for the other two cases. So I'm going to define another method called throw on another thread. And I'm going to use the exact same kind of for comprehension. So I'm going to have fib as io.raiseError with the type int, and I'm going to pass a bunch of exceptions. So I'm going just one exception, and I'm going to use new runtime exception. Let's say no number for you. And then I'm going to call start method on this thing, and I'm going to wait for the fiber to join. So I'm going to have result left arrow fib.join, and I'm going to yield result. And of course I misspelled result. And I'm going to throw on another thread, and I'm not going to pass anything. And we're going to inspect how that looks like. Again, I don't have a run option. That's because I'm eager to... Okay, so we have an errored object here with a runtime exception, no number for you. So this is the second case that a fiber might end with. And now I'm going to also test a cancellation state. Now for that, we will need some temporal aspects of IO. So I'm going to define another method called test cancel. And I'm going to define an IO that takes a second to run so that we can have time to cancel it. So I'm going to have a val task, for example, and I'm going to have an IO, let's say starting, and I'm going to call debug on that so that we can print the starting message to the console. And then I'm going to sequence that. So I'm going to use the star greater than, this is the sequence operator on IOs, and then I'm going to have IO sleep with 1 second. And because, of course, we don't have the second method, I'm going to have to import it. So I'm going to go to the top, import Scala, concurrent, duration, everything. All right, so now I have the 1 second method. And then I'm going to sequence IO with the string done. And then I'm going to call debug on that too so that I can see it on the console. All right, so I'm going to start this task. And then after half a second, so midway, I'm going to cancel this fiber. So I'm going to have for, and I'm going to start a fiber. So I'm going to say fib left arrow. I'm going to have task dot start. Okay, and then I'm going to create another IO which cancels that fiber. So I'm going to have say IO dot sleep with 500 millis, that's half a second, and then I'm going to sequence that with IO with a string canceling dot debug so that I can see this on the console too, and then I'm going to have another result with fib dot cancel right after that. So notice that I can call the cancel method on a fiber, and you'll notice the result in a moment. And I'm going to say underscore, fib.join. So I'm going to wait for the fiber to finish, and then I'm going to call this result. And then I'm going to yield a result. Cool. So this will be an IO. Let's see what kind of result we get. So we have a task that is this IO that prints starting to the console, and then we sleep a second, and then we have this IO done. Now the value contained in this task is going to be this string, but we don't really care about it. But in the meantime, while this task is being executed on this separate thread in a fiber, I'm running this IO with 500 millis, and then I'm going to print this canceling thing to the console. Of course, this IO over here returns canceling, but I don't care about the result. I only care that the fib does the cancel after that, and then I'm going to wait for the fiber to finish, because the fib doesn't really cancel instantaneously. So, with that explanation in mind, I'm going to right click, and I'm not going to find my run option here in my context. I'm going to hit Control R. And let's see what we get. Of course, in main, I haven't called the right method, so test cancel. Then I'm going to right click. I'm not going to find run again, and I'm going to run from my keyboard. All right. So notice that we have starting, and after half a second, we have canceling from another thread, that is the calling thread. And from the calling thread, we also obtain the canceled object. This is the cancel state that the fib ended up with. Now, did you notice that 20 minutes passed already? Now, I'm really having fun, but I'm going to add a break here for now. You've learned about fibers in this video, how they work, what they are as passive entities, not active like threads, how we can start and wait for them, and which states they might find themselves in when they're done. Now, this concept of a fiber is really powerful, and we can run some really magical stuff in a purely functional way on Cat's effect. And I'm going to show you how you can do that in the video that I'm going to post next week, so watch out for that. And in the meantime, let me know what you think of this video in the comments. I read every single one. And if you want to check out my material, follow me on Twitter and LinkedIn for fresh updates. And speaking of material, many of you asked if a Cat's Effect 3 course is coming, and yes, it is. I'm working on it right now as this video is being recorded. And depending on when you watch this video, I'm also going to link you to it as soon as I'm done. Until next time, I'm Daniel, signing off.